How's it going, everybody? So in this video, I'm going to solve some more random LeetCode questions and kind of walk through my thought process for each one. Also, check out my platform, AlgosWithMichael, where I teach you the patterns to solve a bunch of categories of problems. Specifically for my YouTube audience, you can use the code AlgoHelp for a discount on the platform. Anyways, let's get to the video. All right, the first random problem we're going to go over is group anagrams. Given an array of strings strs, group the anagrams together. You can return the answer in any order. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So I've definitely solved this problem before. Anagram problems aren't too challenging typically. Right away, I know that a hash map is going to be needed for this output. So my thought process is I would loop over all of the strings and I would need to have like a unique mapping for each string. So let's look at an example. So let's say we had, nat and tan. My thought process is I could just sort each word, right? So this would sort to ant, and then also tan would sort to ant. So you know that these two words are part of the same bucket. That seems to be the simplest approach. So let's go with that. So the first thing we're going to do is initialize our result. It's going to be a list of lists. And then we know we're going to need a map. And inside our map, so the key is going to be essentially our sorted string, and then the value is just going to be the list of anagrams that are tied to that sorted string. So we can say string, and it can be a set of strings. Just call this map. And now we just loop over our strings. So strs. And so now we need to actually sort this string. And so to do that, we need to convert this string to a character array first. So just say array equals string.toChar array. And then we can just call arrays.sort on the array. And then now we have a sorted string if we pass the array back into the string constructor. And now this is where we actually check if the sorted string currently exists in our map or not. So, or I guess it doesn't matter because we're using a set. So I don't think it matters actually. Oh wait, yeah, it does. Never mind. So we're going to say set of string, and this is the set. It's going to equal map.contains key sorted string. If it exists, then we just call map.get sorted string. If it doesn't exist, we need to create an empty hash set. And then we just say set.add the original string, and then just set it back in our map. Sorted string of set. Okay, so now all of the values in our map should be added to our result. So this should be fairly easy now. I think all we have to do is loop over all of the values, all of the key value pairs in our map. So we can say map.entry string set of string entry set. I'm actually surprised I remembered how to do that. It's been a while since I've had to write that. Okay. And so now we're just going to say result.add. And so it needs to be a list. So I think I can do this. New array list, and then pass in entry dot get value. I hope that works. And then just return our results. let's submit it and see what happens. Okay, I got it wrong. Oh, okay, I definitely see what I did wrong here. There can be duplicate words, and obviously I need to include all of the duplicate words, so I shouldn't be using a set. My bad. Okay. We're going to change this to a list. And this can just be removed. Entry.getValue. And then we'll say new array list. And this will just be a list. Oh, let's call this list, not set. Okay, let's try submitting one more time. Oh, whoops. Nice. One problem down. All right, random problem number 2, unique paths 2. You are given an m by n integer array grid. There is a robot initially located at the top left corner, i.e. at grid 0, 0. The robot tries to move to the bottom right corner, grid m-1, n-1. The robot can only move either down or right at any point in time. An obstacle and space are marked as 1 or 0 respectively in grid. A path that the robot takes cannot include any square that is an obstacle. Return the number of possible unique paths that the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the 9th. Okay, so I've done these. I've done the unique paths one. I think I've done this problem as well. I know it's this is a dynamic programming problem. And I guess like the fact that it says find the number of unique paths, and also that the test cases are generated so that they can be up to 2 times 10 to the 9. That's obviously a massive number. So at least to me, that always indicates that it is a type of dynamic programming problem where you're going to like build off of previous results. So let's go through an example, because I guess what we need to come up with is the recurrence relation, right? For any DP problem, you want to come up with the recurrence relation before you write the code. So let's say, let's just use their first example. So we have 0, 0, and there's an obstacle there. So let's change this to R for robot, and then this will be G for goal. So we want to find all of the unique paths where anywhere there's a 1 indicates an obstacle. So we know, at least from looking at this one, it's fairly easy to see that there's only 2 paths. So you can go the top path and then down, or you can go the bottom path and then right. So there's only two total, right? So 2 would be our answer here, but we need to build off of the previous results to get that number 2. And the robot can only move down or right at any point in time. So let's copy this. And so starting at 0, 0, if the robot was moving to the right, so far it would be on 1 path. So we'd have 1. And then if we moved right again, it would be on 1 path. And then we move down, we're on 1 path. And then we get to the goal. We got to the goal following a singular path. And then we could do the same thing where we go down. So we're on 1 path, 1 path, 1 path. And then since this is the second path that reached the goal, we're just doing 1 plus 1. That would be 2. So I think our recurrence relation would be dpij, so that like whatever current position we're looking at is going to be equal to I minus 1, since that's the row, so that's checking above us, and then the current column, plus dp of the current row, And then we want to check to the left. So that would be j minus 1, the left column. All right. So we have the recurrence relation. So we can start on this. I guess the first thing is let's just get our rows and columns just so it's easy. And then we'll say n equals obstacle grid at 0.length. And so the position where the robot is marked as 0, but we need to mark that position as 1 because that will be the start of our path, right? So what we can do here is we'll say obstacle. Oh, wait, that won't work because currently obstacles are marked as the number 1. So, ooh, okay. I guess one thing that we can do, I don't know if this is good, but we could loop over the grid, and anywhere where there's a number 1 where it indicates an obstacle, we can just mark it as negative because we know that we can't have a negative number. And that would allow us to reuse our obstacle grid as like our DP 2D array. Otherwise, we would have to create an entirely new one, which I guess it's fine. I don't know. Let's just go with that. So we'll say m I++ j is less than n if obstacle grid of ij is equal to 1. Obstacle grid ij just times it by -1, and I think that will be it. And so now when we exit that, now we can say obstacle grid of 0, 0 is equal to 1. Right? And so now we can start looping over everything in our obstacle grid, ignoring anywhere where we see a negative number, right? So that means we're going to need to make sure, like when we're checking in our recurrence relation, if we're looking above us or to the left, if there's a -1, then we would not include that number, obviously. So yeah, let's start. So we're going to start at 1. We're not going to start at our robot. I is less than m. J, oops, this needs to be int. And then int j is going to start at 0. I is less than n, or j, sorry. And I guess if we are currently on an obstacle, we want to just ignore it. So we would say if the obstacle grid of ij is equal to a -1, or not equal to a -1, then we can start performing. Yeah, then we can start looking at it. I guess another problem is we need to make sure we're not checking out of bounds, because obviously if we're on row 0, there is no row above us to check. So I guess I can just loop over the top row and then leftmost column. And anywhere where it's not a -1, I can just mark it as 1, right? So pretty much after this loop, I can say, starting at 0, I is less than m. And then if the obstacle grid of it's going to be of 0, 0, I. And this actually needs to be, we're looping over the column, so it needs to be n. So if it is not equal to a -1, right, then obstacle grid 0, I equals 1. I think that works. And then we want to do the same thing for the left column. So that means we're going to be looping over the rows. So for int I of 0, I is less than m, I plus plus. And then let's just copy this. It's not going to be the exact same, but it's going to be similar. We're going to say I of 0, right? So I'll just make a comment here. So this is prefilling the top row, right? And this is prefilling the left column. And so now we don't have to do out of bounds checks in this final loop. Honestly, if I were in an interview, this is exactly what I would do, because whenever I'm like writing like the most complicated part of the algorithm, if I can find a way to simplify it, I'm going to do it, even if it's like an extra loop. As long as it doesn't affect the time complexity, I personally don't see the problem. So yeah, and this initial 0, 0 equal to 1 can be removed. So now that we've done that, if the obstacle grid of ij is not equal to -1, I guess we don't need to start it. We can start at 1, 1, right? Because we've already pre-filled those rows. So now let's get the top value. Like let's say top, right? But there is a chance that the top value is an obstacle, right? So what we can do here is we'll say top obstacle grid of, if we're looking above us, that means we're doing I minus 1. And we're not going to have an out of bounds check since we did the pre-filling and at j. Right, so this top value, technically, it has the potential to be an obstacle, right? So we could say like, if that value is a -1, just use 0. Like there is no path. Otherwise, actually use that value, right? And then do the same thing for the left. We'll say obstacle grid of I, j minus 1. If it equals a -1, then just use 0. Otherwise, we're actually going to use the value here, right? And now it's just about updating the current position. So dp of ij is going to be equal to top plus left. And then when we exit everything, we just need to return the very last value. So return obstacle grid of m minus 1, n minus 1. Let's see if this works. Oh, I put dp. That's funny. Okay, this needs to be obstacle grid. Let's try it again. Oh, I got it wrong. Oh, okay. That is an edge case I did not consider. So the goal itself is an obstacle. So I'm returning -1. Why don't we do this? We'll say if this is -1, just return 0. Otherwise, actually return the value. Oh, I got it wrong again. It's because the robot itself is blocked. Okay, I should have done like a base case in the beginning of this algorithm, and I'll do that now. I should have thought of this honestly, but that's why I'm practicing. Let's go up here and we'll say if, let's just do a bunch of, base case checks. So if it's null or the obstacle grid 0 or obstacle grid dot length is equal to 0 or obstacle grid at 0 dot length is equal to 0, we'll just return 0, right? And then we could also say if obstacle grid at 0, 0 is equal to a 1, or we're probably going to need, let's do this check after we have our M and N, or obstacle grid of M minus 1, N minus 1 is equal to 1, then we return 0. There can't be a path because there's an obstacle there. So let's try that. Oh, I got it wrong still. Okay. Let's look at this example that they're giving us, because clearly I need the help. So this is 1, 1. Okay, so the path is blocked, right? That makes sense. And then after running the first part of my algorithm, these ones would be changed to negative ones, right? And then the top row would be filled with ones. Oh, I see the problem here. It's because I'm filling the left row with ones, and so it should be blocked there. Okay, maybe the pre-filling was not the right way to go. I might have to just do out of bounds checks. Or I guess like until a negative 1 exists, then I stop pre-filling. So yeah, I think that's what I do. I could say if, yeah, I think I could just do this. Like if obstacle grid of 0i is equal to negative 1, then I need to break, right? Otherwise, just set it. And then the same thing for here, except it's going to be switched. Okay, so let's see if that works. It does. It is just very slow. The time complexity is still going to be just m times n. And I don't think there's a faster solution than that. I think it's just because I did the pre-filling that might make my solution a bit slower, but I think it made the logic a lot simpler. But let's move on to the next problem. All right, the third random problem, ransom note. Given two strings, ransom note and magazine, return true if ransom note can be constructed by using the letters from magazine and false otherwise. Each letter in magazine can only be used once in ransom note. Okay, so honestly, this reminds me of the anagram problem. So it's going to be something where I'm counting each character. So let's look at the third example, since that's the one that returns true. So we have AA and AAB. And we want to return true if ransom note can be constructed by using the letters from magazine. So yeah, this problem is very easy, I think. So I guess all we need to do is do a count of all the characters in magazine, right? So A would have 2 and then B would have 1. And then we need to loop over all of the characters in ransom note and decrease those counts. So since there's two A's in ransom note, this would go down to 0. And since the counts are not negative, that means that magazine had all of the characters that were needed. And this can be solved using character arithmetic. Yeah, this problem is pretty simple. So we could say int letters equals new int of 26. So 26 letters in the alphabet. I literally did a problem like somewhat similar to this in one of my previous videos using like character arithmetic. So we're going to loop over all of the characters in magazine. Length, right? I++. And now we need to increase the count. Magazine dot char at I minus character A increase. We're going to do the same thing, except we're going to iterate over ransom note and then decrease. And now we need to loop over our letters array. And if letters at I is less than 0, it means we didn't have the letters that we need. Yeah, we didn't have the letters that we needed. And we can just return false, otherwise return true. Nice. That was a pretty easy one. All right, next problem, binary tree level order traversal. Given the root of a binary tree, return the level order traversal of its nodes values from left to right, level by level. Okay, so level order traversal, I know you can just use a queue to do this. It's pretty simple. So yeah, we would want, like in this example, we have 3 and then 9, 20, and then 15 and 7. So if we were to use a queue, right, like we would add 3 into the queue, and we would also need a separate list to keep track of. So the queue, 3 would be added to the queue, and then we would need to loop over all of the child nodes and add those to the queue, right? So essentially 3 would be removed from our queue, right? But the children would then be added, and then we'd have, some sort of list that adds that, value to a resulting list. And then we do the same thing. And then, so 9 and 20 would become a new list, and then we'd add the children. So 9 doesn't have any children, 20 does, so we'd add 15 and 7, and then now we have 3 and 9, 20, and then 15 and 7 don't have any children, so we're just left with an empty queue, and then 3, 9, 20, and 15, 7. So yeah, I think I know how to do this one. So we're gonna create a result. And we're gonna need to create a queue. So we'll say queue of tree node. Queue equals new linked list. And so what is our exit condition? I guess our exit condition would be when our queue is empty, right? So while queue is empty, or not empty, sorry. This is where we're going to add. We need to add the initial root, right? And now we can grab our size from our queue, because this is the size is gonna tell us how many times we're gonna need to pull, right? So for an I starting at 0, I is less than size. And now I think it's just a simple pull, right? So tree node equals q.pull. Oh, but we also need the list. We need the actual list. So we'll say list equals new array list. And we're gonna add that value to our list and add our left and right node to our queue if it's not null. So if node.left is not equal to null, queue.add node.left. If node.right is not equal to null, queue.add node.right. And I need to add the list to our result. So result.add list, and then return our result. Let's see if that works. Oh, what did I do wrong? Oh, yeah, I should have done a base case check. Okay. If the root is equal to null, we're just going to return our result. Okay. Let's submit. There we go. All right. So I think that is all the problems I'm going to solve for today. So I hope you guys got some use out of it. Make sure to check out my platform, Algos with Michael. You can use the code AlgoHope for a discount on the platform. I teach you how to solve all of the, patterns to solve a lot of these complicated problems. Anyways, I will see you guys next time.